Hi, welcome back. This is Angela Rasmussen from the University of Utah Department of Electrical and Computer Engineering. I'm going to go over another example for parallel today. So here you see a little bit more complicated circuit with several sources in them and a couple switches. So the first step is still to put it into the final configuration of where the switches are going to be, and then look at the connection between the capacitor and the inductor. So for the final circuit, we will have, if I redraw this again, definitely redraw each time. So looking at this and where the switches would be, and then we are going to look at where the inductor and capacitor are going to be. And in that, we see that the switch is open, or it moves to the other position, to the down position in this left side. So we're going to have the switch in this position at the final time. And then for the switch on the right, it's going to again close at t equals 0. So this one will be closed here also. And then our inductor and capacitance, we can see that they are going to be connected. On the top and the bottom, the colors are going to be the same, and so that means that they are in parallel. So you should find from this that you have a parallel configuration. So we have parallel, and so now we can move to alpha and omega naught, which will then determine what characteristic do we have between these. So alpha and omega naught, we need RTH, and so we can use the same circuit for RTH. And so we're going to put the A node on the top and the B node on the bottom between the capacitor and the inductor, and then all of the independent sources will be shorted, or not shorted, or set to 0. So for a voltage source, when you set a voltage source equal to 0, then you get a wire. And so this becomes a wire, and this becomes a wire. And so our pathway between A to B, we see that we can go here, here, as two separate pathways, and this way. So all three of those will be in parallel with each other. So I'm going to have 1 in parallel with 2 in parallel with 5. So that will be 1 over 1 plus 1 over 2 plus 1 over 5. And that will be 10 over 17. So this gives me a 10 over 17 ohms. And so from here now we can do alpha. So we need to get the alpha for parallel is going to be 1 over 2 RTHC. And so this will give a value of 1 over 2 times the 10 over 17 times the 1 times 10 to the minus third for 1 milli for the C. And we get an alpha of 815 nepers per second, 850 nepers per second. And then for omega naught, we're going to take 1 over the square root of LC. And that gives an L was, what was L? L was 1 millihenry. And then the capacitor was 1 millifarad. And so this gives a value of omega naught as 1,000 radians per second. So that puts us into that alpha is less than omega naught. And so it's going to be underdamped. So an underdamped condition. So with underdamped, I'm going to grab the equation set for underdamped for parallel. And so for this one, we need IL of 0. So the initial value for IL, the initial value of IL infinity, the final value for IL infinity, and then VL 0. So remember, for the initial one, the initial values are taken at time t plus. So initial at t equals 0 plus. So that's going to be right after the switch has moved. So we use t equals 0 minus to find VC and IL. And those are the values that stay the same. And so VC of 0 minus will stay the same for VC of 0 plus, and IL of 0 minus will become IL of 0 plus. And these will look like a current source, and this one will look like a voltage source. So that's how we use those to find the initial values. So going back to the initial circuit, and we're going to redraw this the 3 times. So I'm just going to copy and paste these to get the initial at 0 minus, the initial at, or not the initial at 0 minus, but the values for VC and IL to be able to determine at t equals 0 plus, and then we're going to do the final one. So let's start with the initial. So at 0 minus, again, we're just looking for finding VC and IL. And so with this, we are going to have redrawn the circuit, leave out the switches, leave out the inductor, leave out the capacitor, and then we'll determine what each of those positions will be. And so from here, for the time right before the switch moves. So the time right before the switch moves, the switch will move, or the switch is in this top position for this one, and it is open for this one, sitting a long time a wire, and then this will be open here. So I can see here that VC will be 0 because it's in parallel to a wire, and so that will be easy to find. IL is going to be shorting the 2 ohm, so there will be no current in this branch, and so it's going to be the same current is going to be flowing through this 4 ohm. And so if I put ground here, then I notice that this is 0, and I can say that IL is 10 minus 0 over 4. And so that will give me 10 fourths, or 5 halves. And so that will be my current source value. And then right after the switch is moved to this position, and this switch has closed, so it would be here, and then this is going to be the current source of the 5 half, amps, and then I have 0 volts here. And I'm going to place the ground again here, and we wanted VL of 0. So with the voltage source setting the voltage across the inductor, so VL is this is all the same. And with 0 volts, this becomes the same node because there's no voltage difference between them. So you can see hopefully from that VL will be 0. So VL of 0 will be 0, and IL of 0 is going to be the 5/2 amps. And I think that gives me this value and this value. So now I need to, and this value. And so now I need WD and IL of infinity. So an infinity, or a time, long time, we're going to have again a wire for the inductor, and the position of that left side switch will be in this position, and then this one will be closed, and then I have an open again for VC, and we're trying to find the current here. And so if I ground this, remember that for this IL you're always going to want to leave it as a variable. Ignore that it's a wire in that branch, and then you're going to try and find the other currents and do a current summation. So we're going to need to know the current in this branch, and in this branch will be 0, which makes it easy. So the leftmost current is going to be, and this will be 0 volts. So this means that that current will be 0 minus a -5 over 1, and then the branch with the 2 ohm will be 0 over 2, and then again you can see that that will be bypassed because it's in parallel with the short, and so that will be 0. And then we have 0 from where the capacitor is, and then this one on the right side will be 0 minus 15 over 5. And I forgot to write, and IL equals 0. So I forgot to write the IL one. So you have IL now can be solved. So this becomes 5 minus 3 plus IL. And so IL will be a -2 amps for the final value. So we also need to know WD, and so WD is going to be the square root of omega naught squared minus alpha squared, so that gives me 526.8 radians per second. And I need now DL, go back up to these. So DL was going to be IL of 0 minus IL of infinity. And so we have, for this one, IL was, I think, 5/2. Yep, 5/2. And then we have a -2. So we get 4.5 amps. And then for D2, we had VL was 0. VL of 0 was 0, so that makes that easy. And then we have a plus alpha, which was, where was alpha? 850. So we have 850, and then IL was the 5/2 minus a -2 all over the 526.8, and that gives a value of 7.26. And these are in amps. And then the final equation for IL is going to be e to the minus alpha, which is 850t, and then d1, which is 4.5 cosine 526.8t plus 7.26 sine 526.8t, and then plus or a minus 2. And then we can say that this is IL of t, and then multiply that by U of t. So this whole thing would be times U of t. And this is in amps. Or you can say this equation is valid for t greater than 0. All right, this ends this video solution. Thanks for watching.